Right, so now I'll briefly introduce the work that I've done in the in several months. So this is about solving for a fixed-wing model airplane. So I know a lot of you might at least knew a lot of information about planes, like how they generate lift, how they are maybe how they're manufactured, how they work. But it's a bit more difficult to connect the information and make it apply. So, 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 so for so for designing something, let's just get to the definition of this topic. Because design is just to make some ideas to a real thing. So it's just designing planes involves two things about parameters. For an existing plane, you can solve and analyze its performance, and inversely for the requirements, you could solve for the required performance for the parameter of the plane. And drawing a plane is relatively easy, but solving for that one is relatively hard. And the three problems that occur is first, the amount of variables is too large. Uh, all the aspects you can think of a project, it can be parameters, and thus could be variables or constants. And if I say there's on my hand there's a 100-dimensional place, that doesn't necessarily make sense to you because there are just too many choices to make, and the more choices given, you get a wider range of possibilities, and that's not necessarily a good thing because it make it really difficult to solve for the system. And for the system to work, it must first be consistent with itself, and then it can be optimized to make for a better solution. My suggestion is to use the requirement to start with and solve for a range. So if playing on this 100 dimensional, if a data point on this 100 dimensional place can be projected to some 2D or 3D space, and then I knew the requirements, and they must lie on some range and start with some value, then I can start with a core solution. And by simplification, you could make a core solution and begin to explore more possibilities. And that's what we do with constraint analysis and weight analysis normally. But there's also something involved as in empirical models and empirical data. The second thing is there's lack of data and relationships, because not all the things are deterministic, and sometimes you don't get enough number of independent. You don't have enough number of data input, so lots of things are missing. So to get a core solution, you could get it from constraint analysis or some existing plans, and maybe look at your some existing planes and use their performance as the requirements for your design, because that's if you're clear that this plane is gonna perform better in some ways, then you could actually use the existing parameters as the constraint and solve for a new design. And you can gradually replace the empirical models by more deterministic ones. Now, if the geometric properties are of the plane is given, you could run a full analysis, but it takes more time. If you can estimate that by some models, but these empirical models doesn't it's always deterministic. The third thing is the lack of registration of the target, because you're not really sure. Sometimes you're not really sure what plane exactly you want. Like, I want this plane to be fast, but at some stage, maybe making the plane a little faster could cause a lot of problem for stability, and you do have to consider is that worthy or not. And the same thing happens a lot of times because there are lots of variables and you have to loop for them a lot of times. But with computers, that's relatively easy, especially with programming-friendly packages, and it's it's easier to loop for them. I mean, the easiest way is to loop for them. The better way is to consider the the targets as for some targets, consider something as that you previously think as a constant, as a variable, and actually run the sensitivity analysis. You could do it either by writing a for loop, or you could go parallel, which sometimes hopefully make it faster. So to prove that I'm not lying, is let's just run some demonstrations, and actually we could. So the first demonstration I got here is for the constraint analysis, and for there's one for the real plane from the data is sourced from general aircraft general aviation aircraft design. As if you run this code, you load the library. You also have to load the library first and get the and then you get a default type of input which asks you all of the assumptions that you want, and then I defined I want when it's cruising I want this velocity, this drag coefficients, and lots of initial parameters to start with, and I create something called case1, and let's just see the contents of it. So I must classify it as a constraint, so the create function actually recognizes this, and then I create something called CA1, which is the result of this, and output the result, and we can optimize that at some point. At this point is the thrust to weight ratio required thrust to ratio required with some kind of wing loading, which is the gravitational force divided by the wing's area, which defines its structural properties, and you could plot it and zoom in. You get let's just do this probably. Yeah, looks better. And those are the different constraints defined by different states you get here, and then you get some minimum speed, and this is a sample calculation, which you could get rid of that later. For different plane, you actually get different ways of doing this constraint analysis, but the process are very similar. And for Zhenghan's doing this, I create a create constraint list, and then classify, and then create it, and then I get very the thing is in the same format, and you don't have to worry about the function it calls, the numeric calculations, because it does it for you. It recognizes all of the things that are put that are given, and you can actually see when I input different constraint, they actually give me a different type of sometimes different type of curves, and these patterns are just sometimes really interesting. And you could optimize for, and you could loop for the criticality. Say, if I want this plane to take off within 20 meters or within 1 meter. So if I want this plane to be more portable, and especially when this is a small project, I wanted to be able to take off from a very rough surface, and probably from some off-road condition, I could actually run this. Sorry, we could. Sorry, we will have to load. Let's just do this sequential one instead of the parallel ones, because we still have to load the package. That'll make it faster, but we still have to load the package before we do the parallel computing, and then see the criticality. So yeah, so you have to trade off these things before you actually make the decision if it's actually worthy or not to do this. Right. So probably the time. Oh, we still have time for other demonstrations. So let's just do. So where did I get these things from? This coefficient of drag coefficient and lift coefficient, and the lift induced drag factor. I actually get this from some from databases, and you could actually get it from a lot of places. Like you could generate the polars from virtual wind tunnel, and you could load the result into the package, and then I can find the space where a certain lift to drag ratio occurs. So if I import this, you could use the linear property of thin airfill. Use the thin airfill theory to create the properties. Like I create a property here. It's just very similar. Define, classify, and create, and then you get a matrix of data, and then you could optimize for a certain solution. That's still called optim, but it knows what is optimizing because it's an objective function. And then you could do some 3D plots maybe, and then 2D plots with the optimization, and yeah. And then I could actually load some data. Instead of generating from empirical formulas, I could load some data. If I already selected an airflow, I could load the data from this airflow data, and then I could plot and calculate for some certain interesting points, like this. And you get the CL and CD data, which could be used to put to create a constraint analysis. And then for the analysis, so this software is basically a toolbox. Instead of showing you all the workflow, but we will do some further work on that to make the models more connected. And one of the way of making it more connected is that you actually see analyze the motion of it. So once you figure out the thrust to weight ratio, the thrust, the power, you could define a range of. All right, it's time. So we will do some more demonstration in the next section. Right. So if you want to get this package, there's two sources. I've made a simple website with Weebly, but there will be further information on that. And on GitHub, there's my profile, and you can see all the projects that I had developed, and most of them are open source. Great, thank you.